Welcome to this lecture of operating systems. I think by now we are in the fourth lecture of operating systems already, and today we will start with the virtual memory basics. Let me just move to the right window here so that I can actually click on the next slide. And I'm also opening the Menti already. You can also open the Menti either by entering the code that is cut off up there. Maybe we should fix that. So let me just resize that a bit and then you will be able to read the code. Okay. Yeah, maybe like this. You can also find the link in the YouTube description, so you can also just click that link. Perfect. And I see the first reactions there. So, yeah, I see. That's, this is actually, I wanted to remove this one, so I will directly skip it. So let's maybe go to this slide here and we can start with the content. Today we will talk about address translation, and we will start with very, very simple address translation forms. So very, very simple address translation. Let's start with a very basic idea. And this basic idea is that maybe in previous lectures you didn't always learn the truth of how things are. Some years ago I was also a tutor in ESP and SEP, and back then I also taught how arrays and pointers work. And basically my explanation was that that a pointer is just a number, and you can imagine it like this. So maybe you will have something like the RAM, and the RAM is something like a large array. Okay, large array. And this array has indices. Maybe here, this index, there's some data stored here. Let's say we store a character A here. Okay, let's remove those character dashes because we don't need them. It's a character A stored here. There's a B stored here, C, and so on. Or maybe we store something else here. So if we want, we can also write something like here we store an entire string, maybe here in this memory location. If it fits within the memory location, why not? Now, what I explained to the students at the time was, and I will also open the chat so that I can see your comments there. So what I explained to the students there was that a pointer is basically something that points to somewhere in this RAM. Oh, this is a bit cut off. Okay. I was afraid that this would happen because I don't exactly see where the borders are. So let's write it here. Okay, RAM. And basically if I take a pointer, let's say this is a pointer, and this pointer points somewhere. Let's say the pointer points here. That means if this RAM is just indices, and this is index 0, this is index 1, this is index 2, and so on, that this pointer would have exactly which value? It would have the value, in this case, 1. So far this makes sense, right? This is how you learned how pointers work. Pointers are nothing but numbers that are pointing somewhere in this RAM. And I also want to get rid of this notion of pointing. Of course, you can imagine a pointer of like pointing somewhere, but let's really get rid of this notion of pointers pointing somewhere. It's more about a pointer being a number and telling you where this is. So what you can imagine if you write a program, let me just move some chairs away here, and what you can imagine what a program works like. So imagine you have a program where you access some global variable. Here we access a global variable, global equals 4. I assign this value of 4 to this global variable. Now what you can imagine, what the compiler or what the hardware actually all the time does, given this model, is that this is actually an array access. RAM at this offset equals 4. The RAM is just a huge array. Does that make sense so far? If not, please write in the chat, but this is our most simple model of how memory works. It's nothing to do with pointing around. It's just an index in an array. Oh, I see that my arm is a bit sometimes my arm is a bit transparent, but that's due to the setup with the whiteboard here. Okay, let's maybe wait a moment here, let that sink in a bit. So this is a pointer, the null pointer. Let's try the null pointer. So if we write null here, or we can also write this as a hex number, null. Maybe I should write a bit more properly, but I'm not good at handwriting. I was never good at handwriting, and on the whiteboard it's even more difficult. So 0x0, that's the null pointer, right? And a null pointer points where? Not to this location, of course, but the null pointer is just the pointer that points to this first offset here in the RAM. There's nothing special about this null pointer. Interesting. We could store data there and we could read it probably. We could assign something there. We can at least try this. If we write pointer here, then we would assign this to the null pointer, to offset 0 in RAM. And this is very nice because now we can also think about things like pointer arithmetics. Let's assume that we are actually not accessing global at this directly. So let's assume global is some, let's say it's a character pointer, but we are accessing actually, I will remove this part so that I have some space to write this down. I will actually now access global at offset 7. Okay. Global at offset 7 equals, let's say, again, we write 4 to this location. Because why not? We just write a value there. So this is offset 7 in this global array. These brackets that we see here, what the compiler always does, absolutely always, is it replaces these brackets. So if you take a look at this, you probably still know this from SLP because you have tried it there. You can actually rewrite this code and it's exactly the same. So we write it like this. We dereference global plus 7 equals 4. The compiler will replace this line with this line internally and only work with this construct. Now we know how the plus operator works, right? Does it matter on whether we write a plus b or b plus a? It doesn't, right? We know this much from our math classes. It doesn't matter. So we can try to write also like this. And then we have 7 plus global. That's still allowed. Of course. I mean, why wouldn't it? But if this is allowed, what about this? And you can write in the YouTube chat whether you think this is allowed or not. Should it be allowed? Should it be forbidden? What does it do even? 7 at the offset global. Interesting. Of course this should be allowed because it's all the same. In all of these cases we are dereferencing something, and in the middle two cases we can directly replace it. These brackets, of course, we have to resolve them so that the hardware can work with them, because they don't mean anything for the hardware, these brackets. But this, a plus operator, this is what the hardware can work with. And actually, what we do here is, again, this RAM at offset global plus 7. And then, of course, it doesn't make a difference whether on this side or on this side you write global or 7. So it's the same in this case. It's again an array access to this big array called RAM, and it doesn't matter whether it's global plus 7 or 7 plus global. The same number will be computed here. Does it make sense to you? So this is some part about pointers and how pointer operations work. Actually, when you look at this, so this is true for a character pointer, but actually here you would have to write 7 times a size of global, or a size of global at offset 0, because you need to take the data type into account. In C, this wouldn't work, obviously. Florian, try it out. For the hardware, it doesn't make any difference whether you write global plus 7 or 7 plus global, and this is why this is totally fine. Some compilers don't allow it if you provide some advanced warning options, but in the most general case, this is the same. Okay. So this is pointers. And I hope it's clear now why we don't speak about pointers as they point somewhere, but they are just numbers. Pointers are just numbers in this big array, indices in this big array called RAM. Now, this is what I explained to students at ESP when I was an ESP tutor. So there's a question, am I wrong that C vars are not allowed to start with a number? Yes, but this is not a C variable. 7 is not a variable, it's a number. So this is totally fine. The compiler will search and replace this pattern with these brackets here and replace it with this other pattern that I had on the whiteboard just a second ago with this pattern. Global at offset 7, so global plus 7 equals 4. The compiler will just replace this, search and replace, like a define. And that's why it doesn't matter, because I've shown you that I can flip this around and transform it into this pattern again. But if the compiler just goes search and replace for this pattern and replaces it with this other construction, this much easier construction for the compiler, because it's just a pointer dereference, no fancy brackets or anything. So this is something that the compiler knows anyway. Then you don't have to implement that multiple times. Okay, so now we talked about pointer arithmetics, and I will delete some part of this whiteboard again. This part here, we don't need this part anymore because we have understood why this works. Why pointers are actually just numbers, just indices in a large array. If that's not clear, ask in the chat, because then I will be able to answer your question. Also, I see that there are already questions on Menti. I will also take questions on Menti, but it's easier for me right now while I'm on the drawing on the whiteboard to see the questions in the chat, because for the questions on Menti I would have to get the phone and check out what people are asking there. Okay. So we want to think about a very simple case. And what is the benefit of using 7 global? I don't know, confusing people. I don't know. There's no benefit. I just wanted to show you how turning these two arguments of this array operator around is allowed. But it might depend on your compiler warning options. So in some compilers, this might raise a warning. In some compilers, this might even throw an error. But in the most general case, this is allowed. I can certainly construct an example like that in different compilers. Okay. There's something odd here about this explanation. Because if a pointer is an index in RAM, which totally the teaching assistants, the lecturers in ESP and OOP1 would explain to you, and I think it's the right thing that they do that, then how can something like the null pointer be invalid? Because this points into RAM. RAM is always valid. It's always there. So how can this be invalid? Are there pointers that do not point into RAM and therefore, but pointing, that's again this weird notion. Are there indices that don't fit in this array anymore? But how can it be, for instance, that in the middle there are some indices that are not valid, and at the start and at the end, and in between there are some valid ones? That cannot be explained with a simple array like this. So the question in the YouTube chat is 7 plus global would be the 7th place in RAM with value equals 4. No, it would be you add together the address of the global variable and 7. So you're adding global plus 7. And then dereferencing that location. Let me maybe illustrate that. So let's say global, let's write that down here. Okay. Let's spend a bit more time on this example so that we really got this. We have the global variable here, global, and I will say that this pointer has the value of 6. Let's say, okay, here we are at entry number 6, and now we say, what do we write here? Oh, we need some space now. Let me go and write this down. 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we have a lot of locations in the in this RAM where we can store some data. And probably if we consider these all single bytes, then we cannot store an entire phrase hello here, because each character would have too much data. So we might store an H here, but maybe here a E, 3, 4, 5. Okay. Hello. 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 World. Example. Okay, I don't have space down there anymore, but this should be a hello world example, right? We say global, this pointer has the value of 6. And now we say that we want to access global at offset 7. This global has to be defined somewhere, right? So let's assume this is defined. We probably should do that somewhere. So let's say it's defined as a character array. Character array, global. Do I still have the space? No, I'm running out of space here. Let me write that down again. It's a bit easier on the blackboard in the class where it's very clear where you can write something and where you can't write something. Character, it's character global, and the array size in this case will be, let's say it's starting at 6, so the array size might be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say it's 10. So that would mean that global starts here at this offset, and the last index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here it would end. You can't see down that far down. So it would end a bit further down here. Okay. So this is just the data that I store in RAM. Why is there an A on the base index? That's the data that I write into the RAM. That's if I would look into the RAM, into the chip, that is what is stored in this RAM in this example. because I probably previously wrote it there. Okay, let's take a look at this example again. We access array, this array global at offset 7. What happens? Well, the compiler will not know where this global variable, or maybe it knows where this global variable is, but after all, in the end, the hardware will at some point combine these two numbers if the compiler didn't. And what happens here is the hardware or the compiler will just replace this global here, like in a math equation, and say, well, this becomes 6. That's the value of global 6. It's like a math equation. And the compiler also says, well, let me write that down in multiple lines because that's maybe a bit nicer. So global at this offset. This is the same as I said, it's always, you can always write it like this. It's always this pattern, array name and index. Global plus 7. And this just means that we again compute what it is. So it's 6. So we have here 6 plus 7. And that means we dereference address 13. So the value that we read here is A. Character, if we would read this, we would get the value A. Does that make sense? Are there any other questions that are not clear yet? And now it probably, so I hope it makes more sense to you now why I can also turn these around, because these aren't just numbers. Pointers are just numbers, and I will just take the number from this variable and place it there in this equation. So there's a question in the chat: when global 7 is equal to global plus 7 times size of, that's almost correct. So it depends a bit on the data type of global here. So in a more general case, you would have to write size of global at offset 0 to get the data type size, to get this size here. How do we transform 7 global? Well, it's exactly the same. And there's a question why it says A here, right? I can also write, I don't know, a different letter there. I can write a D there if you want. Now it's D. I can write any value there. Or is the question for 13? Because 13, you can't see this anymore on the screen, I guess. So I have this. Does this work? So here you can see that 13, I wrote A there for my hello world example. But if, yeah, maybe like this. Now you can still see that it's the RAM, and you can also see that it's there. The value is A. Because I read that from this memory location. This reads A. A hello world example, exactly, yeah. But now it's D hello world example because I put a D there, because I can write into memory what I like. Okay, so let's do the same example because someone was asking. Not with global 7, but let's do the same example with 7 global and let's see what happens. But this is math, right? 7 at offset global. This is just adding numbers. And if we do this, let me fill this in here. This is just 7 plus global. And that makes sense. And now this is not 7 plus 6, but it's 6 plus 7. It's 7 plus 6, right? Okay, yeah. If it would be an integer, you can transform it in size of int times, okay, you would have to be a bit careful there. And of course, this is okay. So maybe let's go for one integer example. But okay, how do we do that? Okay, let's make a smaller array. I will make a much smaller array because integers are really, really large. So I will only have space for 2 integers here on the whiteboard. So it's a 2 integer array. Now this changes a bit because 7 at offset global. What do I have to do now? Let's first start with a simpler example that we already know and see what happens. We will now get a different value here. An integer is 4 bytes. So we have to combine these 4 bytes and that might be a bit more complicated, but we will try whether we can do that. Global at offset. We can now decide what do we want, offset 1 maybe. Then we have here global plus. And now you're absolutely right. We now have to take size of int into account. So it's 1 times size of int. So this is now 4. Global plus 4. So this is the same as 6 plus 4. So it's 10. Or let me write that down properly. I only skipped the part with the size of. This is 1 times size of, does it fit there? Size of int. Yeah. 1 times size of int, and that's 4. And then we have here global is 6. 6 plus 4. That's 10. And 10 gives us the value. Oh, now we have to be a bit careful because we have to read 4 bytes at once. So this would give us some representation of these characters D, E, X, A. Okay. I didn't talk too much about what these bytes here represent, so I would have to be careful on what number exactly gets out there, because interpreting integers or interpreting characters as integers is always a bit complicated. You might have heard about endianness here, and I would have to take care about that to do that properly. But it would be the data from these 4 bytes. Okay. So global at offset 7. Global at offset 7 is not O. Global starts at 6. Global has the value 6. This is the RAM. This is not the array global. The array global is just part of the RAM. It's somewhere in RAM. Global is just a number. Only the compiler thinks that this is an array. And maybe you as a programmer. The compiler will replace global with this number here with 6. So 6 plus 7 is 13. Okay, let me turn this example around because why not? So in this case, I could actually here it can get tricky because of pointer arithmetics. So if you have 1 plus global, you might end up at a different offset. So it doesn't necessarily work in the same way for all pointers. So if I would try that, let's try that. What happens? I have 1 and then global. I'm actually not sure what exactly the compiler will do in this case. And I might need a variable actually for this to work, but then it would take the data type of the variable. So let's assume that we declare a variable int I equals 1. And then we take this global, we had the previous example with global I, and now we do this with I global. So in this case, we would again have so let me write that down again. In this example now we would have I plus global, we have global times size of int. Global is now 6, so this changes now a bit where this points to. because this is not a character pointer, right? And then now we have a completely different value here. 6 times 4, that's 24. So this doesn't always return the same value, but it does for character pointers. And then, of course, I would be 1. So it would lead us to 1 plus 24, if I'm not mistaken. And then we would have 25 here, and I don't even know what is written at 25, because I didn't write the array long enough. Okay. Okay, sounds good. Well, let me readjust this a bit so that we are back at the right offset here. And I would say this is already a good start. If we understood pointers this far, we can continue with the next part, remove all this stuff, because there is something odd about this, and we will have to clarify this a bit, figure out what is wrong. The null pointer. How can the null pointer be not valid? How can, in general, there's this other observation. I don't know whether you still recall this from SLP, but I did that in the SLP lecture. I ran 2 programs at the same time, the same program binary, and I ran it 2 times in parallel, writing on the same global variable, but they didn't interfere with each other. Why? Why did they not interfere with each other? Each process has its own virtual memory. Yeah, but what does that mean? They have their own virtual address space, but we don't know even what a virtual address space is. So let's try to construct a very simple first virtual address space. So let's try that. What we want is basically, we have a pointer, and this pointer is passed into some box, and out of this box we get an actual pointer. Let's write it here, actual pointer, and this points somewhere in RAM. Again, I'm also used to this notion of point somewhere, but again, it's just a number. So let's assume this again is a number of 6. The actual pointer might have a completely different value. Maybe this has the value of 17, because why not? Okay, that's too far up. Let's maybe write that a bit lower here. Equals 17. What do we have here in the middle? Well, if I would implement that, I'm not a hardware engineer, so I would say what we have in the middle is a standard map. It's a standard map, right? So what does this mean? A standard map. From what to what does it map these things? So it's a standard map that maps a pointer, so let's say an integer, to an integer. This is a map. We map pointers from this to this. Now, there are different ways how we can implement this map here, and we will go through several of these ideas and basically discuss them. And we do that now, and I go back to the slides for that for a few moments so that I can actually explain these ideas to you in a very nice way on the slides, and then we go back to the whiteboard for paging, which is for paging as we have it today, multi-level paging or address translation, x86 processors as we have it today, because this is then the part that is also most relevant for the exercises. But this, before that, is very important to slowly get there, to slowly get an understanding of how virtual memory is intuitively created. So, address translation. The operating system controls this address translation, this standard map, and this enables a lot of features. I would say this is one of the most important features in modern operating systems, because it enables isolation of processes, it enables sharing of memory, it enables efficient memory allocation, dynamic memory, on-demand memory allocation. So it's responsible for a lot of mechanisms that make computers easier to work with, and at the same time also more efficient. Okay. Yes, from the programmer's perspective, pointers now point to objects, but it's completely transparent. The programmer does not actually need to know how this pointer is converted to an address that refers to some data. The user just does not care about this. And this is pretty much what I've just drawn on the whiteboard. You would have a processor here, and the processor has a virtual address. We split this physical address into this address that we had before. We split this up into a virtual address that we use to work in a process, and a physical address that the hardware can work with. I just called this actual pointer on the whiteboard. We would call this now the physical address. And an address is just a number. So let's take a look at this processor here. It passes the virtual address to this translation map, like the standard map that I've just shown you earlier. And now the map will either say, I don't have an entry for this address, and that means it raises an exception, or it says it's valid, and that means it gives us an index, because the map contains an index for the physical memory, for the RAM. And the RAM provides us with the data, and we can work with the data. Okay. Okay. Everything clear so far? This is a very, very simple idea, very simple version of address translation. And we can implement a lot of things on top of that. Memory protection, memory sharing, shared libraries. Also sparse address spaces. We can make address spaces that are very large, but only a very small part is actually valid. And because someone in the chat is referring to con-tutors, I think the con-tutors will also be more excited the further we go through this address translation concepts. Then, of course, we can have multiple regions, for instance, heaps, stacks. We can allocate all of this in our sparse address space. This allows to be very efficient when implementing things, to be very flexible, because we can allocate small parts of memory to some task, to some thread, to some process. We can at runtime modify the mapping, look this mapping up, and get the data. And we can also try to make these translation tables very compact, so that it's also efficient to implement. Portability is also one important part here. If you write a program, you don't want to write it in a way that you have to take every processor architecture into account, but instead the compiler should be able to work with virtual memory, virtual addresses, and the operating system should make sure that it translates well to the physical addresses on any hardware. Let's go for the most simple version of virtual memory. In the most simple version of virtual memory, we don't have a very complicated map. We have a very, very simple map which only stores two things: a base address and a limit. Similar as the segments that we've got to know during the boot process, but much, much simpler. So this is how the processor thinks this works. Right? The process, if you run a task on your processor, it would work with virtual addresses, and it gets data from this virtual memory. But what actually happens is that this virtual address is combined with the base address. We add this together, and then we look at up at this location. Also, we can have a bound, a limit. So that means that we can, for one process, define this base and this bound, and the process can only access data in between this base and this bound. So that means we can have multiple processes that are isolated from each other in this physical memory, because we can give them different areas with different bases and bounds. If it's outside of this bound, we will raise an exception and will maybe kill the process if we want to. Okay, let's talk about this a bit more. Now we have virtual addresses. Virtual addresses start at address 0 and go to an upper bound. The physical address then, because this is so simple to translate, go from base to base plus bound. Very easy to translate, just an offset. The question that I have now for you is, what is saved and restored on a context switch? What do we have to save and restore when we switch from one process to another? And I also have some more things here, but you can already think about that and write that in the YouTube chat. And in the Menti, I have prepared another nice thing here. I want to brainstorm with you what are the advantages and disadvantages of base and bound. And you can write that down in the Menti, what the advantages are, what you think. Security. Security is an advantage over not having base and bound, yeah. Fast, yes, this is very fast because we just need to add two numbers. In many cases, we might be able to do this even with a simple, maybe with an XOR or with an OR operator, not even a full adder. But a comparator, we probably need to compare whether it's out of bounds. It's very fast. It's very easy to understand. Disadvantages, no dynamic change. Yes, we cannot easily dynamically change that, because what happens if right after this area some other process is already starting? So this is very easy, very fast, very simple. It provides a security feature, but at the same time it has several disadvantages. Not being very flexible, not allowing any dynamic allocations. Okay, let me switch to the Q&A for a second, because there are already quite a lot of questions. Is A1 already published? Yes, it's on the website. When will we get our repositories? I hope this week, but I will check. But I don't create the repositories, so I also only have to wait there. When an interrupt occurs, we spill registers to the thread's kernel stack, but we said the same about the TSS. How do they interfere then? The TSS stores the pointer of the kernel stack. It stores the address of the kernel stack. So when we have a context switch, the processor will take the TSS, because the TSS is loaded into the CPU with this global descriptor table, so the processor and also with the load task register. So the processor knows exactly where this is, but it doesn't know where our kernel stack is. So the processor checks the TSS and loads the kernel stack pointer into the corresponding stack pointer registers upon the context switch, and only then it stores data on the stack. Regarding yesterday's session, where from does the kernel get the address to the stack of the new thread on a context switch? Is it saved in the PCB, TCB, or the TSS? In the TSS, we would have the address of the interrupt stack when we switch into the kernel. In the yeah, more or less directly in the process control block or process list or thread list, we would have probably some thread object, and this thread object has some member variable where the stack pointer for the user space stack for this thread is stored. So you would get this from a member variable from within the thread. Okay. So where do you live? Because the background sound is pretty loud. Actually, the background is, so for me, it's actually totally quiet here, but the microphone seems to pick this up pretty badly. Let me just check whether I can also reproduce this locally, so whether I also hear this, whether I also hear the sound noise, or whether it's an issue on some other side. It doesn't sound too bad on my side. It might be the amplification of the sound though. Okay, I will close the door later, but it's getting pretty warm here with the lights and everything. So that means that we map data between base and bound. But how does the illusion of unlimited memory really work? Or am I missing something? Yeah, this is not very good at creating this illusion of unlimited memory. It's actually pretty bad. Are there only processes for user space or also processes for kernel space? You would usually only have user space processes. In the kernel space, you have kernel threads. You have a lot of kernel threads, not just one. You have, in modern operating systems, you would have hundreds of kernel threads possibly. Please consider teaching ESP and OOP1. So the problem is, yes, I really like teaching. I really enjoy teaching, and I want to. That's why I stayed in academia. And I would love to teach a lot of different subjects, but I can't teach everything. I don't have the time for that. Does it make sense to also split the thread class into kernel and user thread? I would not do that. I don't see an advantage of that. You can do that, but I don't see an advantage of that. No background noise, okay. Yes, we already answered this. This returns, both return 4 with GCC regarding your example. Okay, let me think why this is happening. So we have array 3 and 3 array. So what would happen here in this example is that it should yes, of course. You're absolutely right, because what happens here is that this array here, we have to be a bit careful with the braces here, with the parentheses here. Let me write that down again, just on this whiteboard here. So let's assume we have this integer pointer, integer, let's say integer array A, and this has 2 elements, and these 2 elements are 0 and 1. Okay. Let's assume we have this. Now, if we access A at offset 1, this would be the same as accessing A plus 1. But the thing is that A is still an integer pointer at this point. So this is why the plus operator now, when we resolve this, this would be A, or actually the value of A. Let's assume the pointer A has the value, let's assume it has the value as before, null x 6, hexadecimal 6. Then but it's the same as decimal in this case because it's a very small number. So then we have, if we resolve this, as soon as we insert this number here for a, we would have to also resolve the plus operation, because this is pointer arithmetic, and at this point we would have 1 time size of a at offset 0 to get the data type of a, and that's the same as size of int in this case. And a is now inserted here, so it's 6 plus 1 times size of int. Okay, and now if we turn this around, this would, and yeah, we can also resolve this, so this is 6 plus 4 then, because it's 1 times 4, so it's 6 plus 4 equals 10. Now let's turn this around again, just so that we also have done this correctly in the lecture. I will turn this around, and now I will access 1 at offset a. And now you will probably already see what is happening here. So now I have 1 plus a. But the thing is, a, the variable a, is still defined as an integer pointer. This is still an integer pointer. And if we add 1 to an integer pointer, it still uses the same arithmetics. And the only thing that changes now is the order of operations here. So this is this plus 6. This is 4 plus 6 then. And this equals 10. Oh, you can't see the 10 anymore. But I actually wrote that down there. I should draw myself a line somewhere here so that I know where it's cut off. Yeah. Oh, actually there's a bit more space there. Okay. Perfect. Let's continue with some more virtual memory. I hope that was clear. Yeah, they are both converted into pointer arithmetic. That's the reason. Let's first go through the questions. We have a few more questions, 6 more questions. Okay. So this is clear now. Before I added the pointer arithmetic at the wrong offset, I think, at the wrong step in this operation. Do kernel threads need a loader, since the loader is part of a process? You need a loader when you need to load a user space binary. Do kernel threads need a user space binary? If they don't, then they don't have one. You can also take a look at kernel threads. Take a look at, for instance, the process registry thread and check whether it has a loader. In SWEP, is the process registry basically the PCB? Yes. It is. You're correct. Is the timeline on the website up to date, since debates are 1 week ahead of submission POC? Yes, that is correct. Because you want to get the feedback from the debates to incorporate in your POC. Are the updated slides already on the website? I can only find the slides from the last 2 semesters. I haven't uploaded them yet, but actually I didn't change much. I actually only removed a lot of the history slides because I found them less interesting and thought we can cut a bit away there. I think the earbuds are then corrupted. Okay, good that we found the problem. The current directory is part of the processes, actually, according to the let me read that again. The current directory is part of the processes, actually, according to the manual. Okay, yeah. But we need it with kernel threads. It depends if you, okay. Maybe maybe we should take a step back here and think about this. This is referring to the man pages, I think. Man pages are first of all Linux specific, and man pages are always written from a user perspective. That's similar as the POSIX standard. The POSIX standard largely makes no assumption about whether there is even a kernel. You could even write in most parts, or even in all parts, a POSIX compliant system that does not have a kernel. You can write something, for instance, you could call it a library OS. Many of the things in the POSIX standard actually are written in a way that library OSs become possible, that you implement all the parts in a library instead of an actual kernel. So this is this is basically how the POSIX standard sees this. So the POSIX standard will not tell you how you have to implement that. And in SWEP, you need the current directory because there's also this virtual file system, and you need to, when you want to open a file, even if you're a kernel thread, if you want to open a file, you need some current working directory so that you can interact with the virtual file system, so that the virtual file system knows what you are referring to. Why is get thread state protected in threads class? So that it can be accessed by other classes. That's why you would mark something protected and not private. What does the loader do? The loader loads pages from the disk into the memory so that it then can be used in a process. And then, okay, last question maybe. Do user threads of the same process use the same binary file? User threads of the same process use the same binary file? Yes. If yes, does only need the process a loader? Yes, only the process needs a loader. Yes. Protected functions cannot get accessed by the child instances. It depends on what you declare as friend. So if you have a derived class and declare it as friend, then you can access this method. But you can change the design as you like. It's your operating system. You decide what it will look like. Let's continue with this presentation. So we do a small change now to this base and bound, and this is what we then call segmentation. Let me maybe move one slide ahead so that you can actually see the slides better. A small change. Okay. A small change, you now have multiple pairs of base and bound registers. And this is what we call segmentation. Each entry controls a portion of the virtual address space. And if you take a look at how this works, you would have the virtual memory. You might have a segment for the code, a segment for the data, a segment for the heap, a segment for the stack. And pointers in there have nothing to do with each other. So you can have a null pointer in the code segment, you can have a null pointer in the data segment, in the heap, in the stack. You can have a null pointer in each of these segments, and they have a different meaning. Because, that's why we look at the implementation here, the processor takes this virtual address, which consists of the segment selector, we have seen that also in the code already, and the offset, which we usually refer to as the pointer. And with that, we take a look into the segment table, get the base and the bound, check what permissions we have. We can now even add permissions here, read, write, and then we can add this base again to this offset and check whether it's in the bounds. And if it is, then we access this data here. This is really nice because now we can actually have something more dynamic. We can have a heap segment, and this heap segment can then grow. If we have it here, the heap segment might be able to grow. Very nice. Still, we have some problems. A segment is still a contiguous region in virtual memory. That means it's one block of memory. There's nothing in between. It cannot be split. Each process also needs a segment table in hardware because the processor needs to interact with that. And an entry in this table would be a segment. Segments can be located anywhere in the physical memory based on this start, length, and the access permissions, the base, and bounds. We now run into a new problem that we didn't have with our previous implementation, with our simple version. We now have the problem of fragmentation. So the segmented memory has gaps. That means that between the code and the data, there might be some free space. Maybe not, maybe there is. Yeah, in virtual memory, it's even that the pointers in the code segment, in the data segment, they don't have any meaning. They might code segment and data segment could possibly overlap, but they don't have to. And the pointers in there are just numbers, just offsets within this area of memory. Now, what if the program tries to load data from such a gap between code and data, for instance? What happens? What do we get? And this is where the name comes from. The segmentation fault. We trap into the operating system and we ask the operating system, oh, can we access this location? And the operating system says, no, it's between two segments and you are not allowed to access this. So this is where the name segmentation fault comes from. From segmentation, correct programs will not generate references outside of valid memory usually, but there are some cases where this might still be reasonable, and we will talk about them in a second. Trying to read or write memory that does not exist might be a bug. So a segmentation fault is actually nice for us because it tells us there is a bug in our code. Does a segment itself have to be contiguous in physical memory? Yes, it does have to be contiguous in physical memory. And that's because we only define base and bound. No possibility to split this up. We can also implement shared memory on top of that. So let me just get something to drink. Okay. Shared memory. We can share segments or even maybe parts of segments. For instance, if they have, if you want to have a full overlap, you can have the same start, same length, same or different access permissions, but you can also make them partially overlap if you like. So you can have a segment which in one process you have 1 megabyte mapped, and in the other you only have the first half of it mapped. How would you use that? For instance, for code segments, this totally makes sense. Let's assume you have a binary, you start it multiple times. Every process could use the same code segment. Very nice. Or for shared libraries. All of them can use the same code segment for this shared library. You can also enable something like inter-process communication there. If I write something to this shared memory location, another process can read it from there. Or another mechanism, and we will talk about that more today or also maybe next week, because tomorrow we will talk about the first assignment. That's copy and write. We will briefly go through copy and write now, very briefly, but we will go through that in more detail as soon as we have understood paging, because then we can build a more powerful version of copy and write. Copy and write is a special type of shared memory, and you might know this already from fork. When calling fork, then the pages or the memory of the two processes might be shared memory, because the two processes have basically the same program, basically the same code, basically the same data. And if you call fork, why wouldn't you mark this all as shared memory? So it does make sense to not copy everything. You just set everything to shared. Yes, the only thing that we need to know then is if a process writes to segment and tries to change the content, then we should not allow that, because otherwise we would have memory corruption in one of the two processes, the one that did not want to write. Reading reading is not a problem. We can always read from this segment and it will not cause any problems for us. But how do we know when a process writes to a segment? We mark the segment as read-only. And as soon as someone tries to write to it, we get a segmentation fault. But in this case, the operating system can decide this segmentation fault is fine. I will copy the segment and mark it as writable. How does this work? So when we call fork, we copy the segment table into the child, the entire segment table with all the base and bound values. We mark in the parent and the child process now these segments as read-only, so that no one can write to it anymore. Then we start the child process and we return to the parent, and both of them run then. As soon as one of them tries to write, it's read-only, we get a segmentation fault which traps into the kernel, it jumps into the kernel, into this interrupt handler for the segmentation fault. And there we make a copy of the segment and then continue. We can imagine it something like this. So we have two processes here, process 1 and process 2, and you can see that in the beginning they have maybe the same value for the same virtual address, for the same offset here. And as soon as one of them tries to, so reading is fine in this case, but as soon as they try to write to it, and this happened already in these cases here, then they duplicate their memory segments here. We can also implement something similar to copy on write, and this is something that we today more commonly use under the name of on-demand allocation. So we will allocate memory on demand. And you could, if you talk about segmentation, you can also call this zero on reference. The question is, for instance, that I need to answer here is, how much physical memory does a process actually need for the stack or the heap? This is runtime determined, so we don't know how much memory we will actually need. Basically we always want to just provide the memory that we actually currently use. And when do we know that the process needs more stack or more heap? Well, the process tries to call more and more functions, putting more and more values on the stack. At some point, this will lead to a stack overflow. And in this case, this might be fine because we exceed the segment size, we get a segmentation fault, and the operating system can go and solve that and just make the stack segment larger and let the process write there. When the program uses memory beyond the stack, segmentation fault, kernel allocates more memory. The question, of course, is how much, but probably just as much as is needed right now, only a small amount. And it's called zero on reference because then at this point we set this memory to 0. Why do we do that? I already mentioned the example with GPUs where you first browsed some website and then played a computer game, and during the loading screen it would still show the contents from the website because they were still in the frame buffer. This is important, zeroing the memory to avoid accidentally leaking information. And then we can modify the segment table, mark the segment as read-write, as read-only, whatever we need for this segment. Probably read-write. If it's a stack or the heap, then it's read-write. If it's another segment and we are just reading, for instance, in the BSS segment, it might be fine to first mark it read-only, but in other cases we might have to mark it read-write. Then we resume the process and continue. Okay. The next step is probably one that I want to do on the whiteboard with you, because I really like to go through this part on the whiteboard. But before that, I have another Menti prepared for you. I want to know the advantages and disadvantages of segmentation over base and bounds, but also in general. What do you find positive about segmentation? What do you find negative? And while you are answering this, I will already click on the Q&A for a second. I guess not, but it's fine. So the segment is all virtual data combined, code, data, heap, and stack. They would all be separate segments. You would have a code segment, a data segment, a heap segment, and a stack segment in this model. But you might even have multiple different data segments for different parts of data, different types of data. You can have as many segments as you like, basically. Maybe there's a limit, maybe there's something like 256 segments. It depends on what the hardware would implement here. But basically, you would have many segments for all the different things that you need to take care of that could dynamically grow. With copy on write, do you copy the whole segment when written to? In this simple example, yes, you would have to copy the entire segment as soon as it's written to. Would you copy all segments at once? I don't think you would, because it doesn't give you any advantage. Can segments really grow, or do you just add more segments? The thing is, if I have a heap segment, I need to grow the heap segment because I can't just use a second heap segment. As I said, pointers in different segments, pointers are numbers. Pointers are just indices, and now they are not indices in the RAM anymore, but within these segments. So they are indices within these segments, and these indices have nothing to do with each other. Imagine you have two arrays and indices in these two arrays, and you want to mix them together. That doesn't make any sense, because the two arrays have nothing to do with each other. So you would have to grow the heap segment. Can segments really grow? Yes, that's a very good point. You might run into a limit there. Yeah, there might be something in the way. Is it one code segment for all processes? I would say, or each process one code segment. I would say that you could use the same code segment here for all processes that execute the same program. But we are talking here about a more historic model. This is not how computers do it today, because we will very soon talk about paging and page translation, and there this all becomes a lot easier and more fine-grained. But in this simple model, you would have a code segment per program, basically. How can you have multiple null pointers in different segments? How do you determine the segment from the null pointer? So the segment is always determined from the type of access that you perform. As we've seen on the previous slide, you combine always some segment selector with some offset. And the segment selector tells you which segment is selected. And the offset, of course, you can have an offset of 0 in different segments. And this would be then null pointers. Okay. What if I want to grow a segment, but there already is a different segment adjacent to it? Oh yes, you ask the right questions, and this is maybe a drawback that you identified here. According to the website, the assignment 1 tutorial is today. Does it start when we are done with the material? Actually, in the assignment 1 tutorial, we will talk about paged translation, about virtual memory with paging. And to do that, I thought it makes sense to first introduce the theory of that and then talk about that for the practicals. So that's why I scheduled, I probably have entered this incorrectly in the timeline or in TUG Online or both. But I thought it makes more sense this way, because we can build up the knowledge this way in a more coherent way. Let me go back to this segmentation word cloud. Yes, we have now separated data, code and data. This is nice, because now we can have data and code that have different semantics. Maybe we have non-executable data. Maybe this is supported now. Fragmentation becomes a problem, both internal fragmentation but also external fragmentation. If you have a large heap segment and there are now a lot of free spaces in this heap segment, this cannot be used anymore, this memory. But also external fragmentation, the space between the segments that you need to keep free so that you can at least grow the segments a bit. Not a lot, but at least a bit. It's more flexible than base and bounds. It gives you more security than base and bounds. It gives you a clear separation, yes. It's more dynamic. You can use faults to implement very interesting features. Yes, you're absolutely right here. It allows inter-process communication. But it also comes with a lot of drawbacks. It's still, as we just heard in the Q&A, it's still a problem. There could be another segment already, and we might not be able to grow the segment. How do you determine the segment for the null pointer? There is one null pointer for each segment. The null pointer is a pointer, let me write that down. If you have a variable, let me write that down. So you have a variable here, let's say the variable is called pointer, and pointer has the value null. That's a null pointer. And this pointer could be a code pointer, it could be a data pointer, it could be a heap pointer. It depends on how you use it, on which segment this will use then. There's also a question in the YouTube chat. So for a new process, we allocate its segments, and whenever the process gives us virtual addresses, we look up its correct segment and offset and map that virtual address to a physical address. Absolutely correct. You fully understood what we are talking about here. Perfect. Okay, let me remove this. Okay. Could you please again explain segfault? I didn't get it well. Okay, so we have these segments and we have a base and a bound for each of these segments. If I try to access an index, let's assume I have let's maybe write this down as an example, and for that I will hide the Q&A again for a second. Okay, if I do that I can actually, okay, I can't see let's do it like this. Okay. So let's assume we have a segment, and this segment, let's say it's a code segment. So this is the code segment, and it has base is, I don't know, take a number 20. Base is 20. And bound or limit, I don't care whether you call it bound or limit, is, I don't know, let's say 10. So let's take a look at the RAM now. This is the RAM. So this segment would go from here. This is 20. Here we have 0. And it would go to 30. So this would be the code segment. Okay, how do we draw this? Base is here, bound is here. Now let's assume that I access a pointer. Pointer has the value of 0. That's totally fine. Then I do pointer plus base, and that equals 20. See? And that means we access this location here. Totally fine. Okay, let's say we access a pointer that is 77. And this will change, of course. Okay, let's remove this. So, okay, 77 plus 20, that's 97. And that would point somewhere here. And this is not allowed, because this clearly exceeds the bound. Because the bound, the effective bound, would be then 30. 30 is the upper limit. This is too large. Okay, I hope this answers the question. If not, you can always ask another question. And the question, let me just go back to this for a second, because the question was whether I can explain a seg fault. The processor checks the bound, checks, oh, this is out of bounds, because let's write this maybe down in a different way, 10, or let's say it's, if you add this base, it's bound is 30, so you would define this in absolute numbers in this case. Doesn't really matter whether it's relative or absolute numbers. And in this case, 97 is greater than 30. So what the CPU does is it raise seg fault. This is how we get to a seg fault. The CPU realizes this should not be part of this segment. It is not part of this segment, so it's a seg fault. Okay, let's hide the Q&A again and let's go for the next concept. And for this we will actually use the whiteboard a lot. And we will think about page translation. And we will now very intuitively derive how page translation works. We still have 40 minutes. I think this is good. We will end up with the first version of page translation, and we will have a nice understanding of how this works. So let's start with a very simple example. So we want to we take the virtual memory here. Okay. This is the I hope you can read this, the virtual memory. And I draw some physical memory up here. Okay. This is the physical memory. And we also have some pointer. I will draw the pointer here. This is the pointer. Let me write that down here, pointer. Now, this mapping with segments or with base and bounds, all of this is super unflexible. We want something that is more convenient, and the most convenient that I would see is if we take 1 byte here, okay, 1 byte here. So this pointer actually so the pointer is pointing there. So let's say pointer, it has the value so that it points here. And I want to have some map so that this goes in here and we get some physical address out if it's valid. If it's not valid, then fine, and we don't get a physical address. But if it's valid, we get a physical address. Okay. Let's talk about the sizes. And I think if you want to decide the bit size of this computer, we can either do this for 32 bits or for 64 bits. I think 32 bits would be nicer. Does anyone have a different opinion? I think 32 bits is nicer for the start. Let's go for 32 bits because it's smaller numbers, it's easier to compute. Okay. 32 bits. What does that mean? That the virtual address space is 32 bits. It goes from, let me write down the 0 up here. It goes from 0 to 2 to the 32 minus 1. How much is that in gigabytes? It's 2 to the, let's go and do that again. We have to be able to translate these numbers into gigabytes and megabytes. So this is 2 to the 10 is a kilobyte, 20 megabyte, 30 gigabyte. 2 to the 2 is 4, so this is 4 gigabytes. So instead of 2 to the 32 minus 1, we could also write here 4 gigabytes minus 1 byte. But of course, the first byte that is not in this virtual memory anymore is 4 gigabytes, because we start counting at 0, right? 4 gigabytes of virtual memory. And in the physical memory, let's start with a simple example. So this will also be 4 gigabytes. So we have here 0, and then we have here 4 gigabytes. How large is a pointer? Does anyone know how large a pointer is? Just write it in the chat. And if you realize that you have a lot of delay, it might make sense to click the live button so that you can that you are back live and can interact with the lower latency. Sometimes YouTube builds up some latency. 4 bytes, 8 bytes. Okay, interesting. 4 bytes. Let's think about that. To store any address in this virtual or physical address space, we would need to be able to address any byte, and there are 2 to the 32 different bytes, and that means to be able to index any of these bytes. It's still we're still in this notion of a pointer is an index. This is still true. Pointer is an index. So far we haven't learned anything else. A pointer is an index, and that means that sorry, I got some of the paint in the eye, I think. Not very nice. Architecture dependent. Yes, but in this case, we already selected that we have 4 gigabytes of memory. So it's not architecture dependent anymore, because we decide, or maybe it's architecture dependent, but it's not unknown. And many people already wrote in the chat, it's 4 byte or 32 bits. This is absolutely correct. So this pointer has to have 32 bits. 32 bit. And we need 32 bits here, 32 bits here. Let's assume we take a very simple map, a standard map, like in C++. Let's do that. Let's see what happens then. Okay, simple map, and this is a standard map. Standard map. What else is 32 bits? An integer. So we can just say integer. Right? Very nice. Okay, very nice. In our case, of course, we don't want to keep integer here, because integer, if it doesn't fit the right size, then it is a bit unfortunate. So let's make this a map from a pointer to a pointer. Pointer to pointer. And then we could say something like, this map is called virtual memory. Okay. VM at offset. And here we can put our pointer. And this would be the, let's say, the fizz address. Fizz address equals fizz address. Okay, so we just create a map like this. What is the size of the map? How much space do we need per entry of this map? And we then probably have to think about where to store this map. If the map could be a bit large, we probably have to store it in the RAM, because it doesn't fit in the CPU anymore, because we will have a lot of entries in this map. Okay, that is correct. 64 bits, at least 64 bits. So this means to map 1 byte here, that's 1 byte, we need 8 byte per entry. Okay. That means for every byte of memory that our process uses, we have 8 bytes of overhead. Sounds good, right? Can we sell this? Will anyone buy that? It doesn't sound that efficient, right? Okay, what else can we do here? Let's think about what we can improve here. So this is really unfortunate. Let's imagine I have a process with a process that uses 100 megabytes. It will need 800 megabytes for this map just to allow me to access 100 megabytes of memory. So this really doesn't look very efficient. It sounds stupid, but maybe we can improve this a bit. There's a question in the chat: why 8? I think I got the tutors back here. So we have the 1 byte here. This is the 1 byte in our virtual memory. We want to map this to 1 byte here in the physical memory. The pointer is 32 bits. Both a pointer in our virtual memory needs 32 bits to be able to index any offset in this virtual address space. But in the physical address space, we also need exactly 32 bits to be able to access any index. And that's why we need 4 plus 4 bytes. Oh yeah, it's totally fine that I was not referring to that, but I was referring to the comment on that this is boring for the tutors. And I think at this point it might get interesting for the tutors again. Okay. So 1 byte of memory, we need 8 bytes of overhead. Is that clear why? If it's not clear, please ask, because this is important and we will now need to improve this. And you can already think a bit about how we could improve this. And while you do that, I will just show you the Q&A again. And here it says, so in your code segment example, the null pointer of the CS would be 20. No, the null pointer in the name has that the value of the pointer is null. Null pointer doesn't mean nothing else but that the pointer has the value 0, null. In what cases seg faults occur in SWEP? Seg faults today, we very often call something a seg fault when we actually don't mean a seg fault, because segmentation doesn't play an important role anymore. But we will learn that there are new types of faults and they are commonly called seg fault. I still don't get why we need at least 64 bits and 8 bytes. It's the same. We don't need 64 bits and 8 bytes. We need 8 bytes. 8 bytes is 64 bits because 1 bit is 8 bytes. So we need 8 bytes. Why do we need that? Well, in this map, we said that we store, let me show that again. We said that we store a map from pointer to pointer. So we have to have entries that store these tuples pointer to pointer. And this is 4 bytes. And this is 4 bytes. So if we have 4 bytes here and 4 bytes here, that makes 8 bytes. I just add these together and this makes 8 bytes per entry. Is it more clear now? Okay. One person says not clear. If it's clear now, if it's still not clear, just ask again. And if you can phrase this into a question, how I can explain it, then I will be able to explain this a bit better. Aren't the first few pages usually regarded as null pointer when trying to dereference? Oh, you can't read the. Sorry about that. Aren't the first few pages usually regarded as null pointer when trying to dereference them? When searching for bugs, the reason for a crash might be the null pointer, even if you didn't dereference the null pointer directly. But we are here talking about the actual pointer values, and there the null pointer has exactly the value of null. But of course, in a real program, you might have an array access, and then one of these pointers that goes into this array access is null, but the actual address that is accessed might not be null, but it's still a null pointer access in terms of code, because you had at some point some null pointer flowing into this equation. Okay, let's why do we combine these 4 bytes? This is a map. I don't know whether I get this question. If I want to have a map where I can look up with a pointer, the pointer has 4 bytes. I want to look up this pointer in this map, and I want to get a value out there that has 4 bytes. If I put in a value of 4 bytes, want to get out a value of 4 bytes, then I have to store tuples of 4 bytes and 4 bytes in the map. Otherwise, I don't find this 4 byte value. You can't see the whiteboard. I have to switch from Menti to whiteboard. This is actually not very convenient. So this pointer here, this pointer here has 4 bytes. I want to search in this map for this 4 byte value. So the map has to store these 4 byte values, and it has to store for each of these 4 byte values a 4 byte value that I then use to look up in the physical memory to get the data from the physical memory. So it's 4 bytes plus 4 bytes, that's 8 bytes. In the chat, there's also comments, 4 bytes in virtual memory, 4 bytes in physical memory. Yes, this is the amount of memory that we need to store the pointer. The pointer has 4 bytes. The pointer is a number. This number has a size of 4 bytes. This pointer has a size. The size is 4 bytes. It's a number. We need to store this number somewhere. We can't just magically say, oh, this is a pointer. It doesn't need space. A pointer needs space as well. It has to be stored somewhere, and it needs 4 bytes in this example because we have a 32-bit system. What does the 1 byte mean? We are accessing a single byte here. We care about the case where we want to access 1 byte here in the virtual memory. So this is the case that we are currently looking at. 1 byte here, 1 byte here translates to 1 byte. This is also 1 byte. Okay. Then there's more questions in the YouTube chat. Okay, I won't read this one because I will get to that in a second. So we are looking at 1 byte in virtual memory, yes, but with a 32-bit 4 byte address, yes, because we need to be able to find any byte in this virtual memory, and it has 2 to the 32 bytes. And to be able to think about, if you have an array that has 2 to the 32 elements, how many bits does the index need to be able to access any offset in this array? And then you need, if it's 2 to the 32 bytes, you need 32 bits. Yes, we are trying to figure out the physical address of a specific byte in memory. A memory address has 4 bytes. Yes, absolutely correct. And I will go for a few more questions on Menti. There are a few more, and I do realize that this part gets difficult. A lot of people struggle with wrapping their heads around this concept of pointers, of virtual memory. So I do realize that this is complicated, and we should not rush through this. So for instance, for the boot process, there were some parts where I went through rather quickly, because the complexity here to understand the boot process is not the problem, and it's just a chain of operations that we have to perform. Here, the complexity of understanding, wrapping your head around this is a lot more significant. Why do we combine these 4 bytes? This is a map. Yeah, because if we want to look up a 4 byte value in a map with a 4 byte index, then the map has to map 4 bytes to 4 bytes. So the null pointer maps to 20 in RAM. Yes, in the example that we had before, the null pointer had a value of null. The base was 20, and that means it mapped to 20 in RAM. Yes, absolutely. At the left side, it stands 1 byte. Yes, if you, I will show the whiteboard in a second again. Yes, on the left side it showed 1 byte. and the 1 byte is the 1 byte that we want to access. This is just the granularity in which we access this. So the map is stored in the physical memory and has 8 bytes overhead and 1 byte for our virtual data. No, it has 8 bytes of overhead. That's it. For every 1 byte in our virtual memory that we map to physical memory, we will have an overhead of 8 bytes, because for each 1 byte we need 1 entry in this map, and each entry has 8 bytes. I think a lot of us didn't get the bit-byte conversion in the example. Have I been jumping too much between bits and bytes? So if there's anything unclear, then maybe we need to repeat it a bit, because this is really crucial that we are all following here. Why do we use pointers as key and element for the map? Because we want to map from pointers, from virtual addresses, from pointers to physical addresses, which are also pointers, but a different pointer in physical memory, pointer in virtual memory. So that is why we use pointers as key and as value in the map. So you just meant that size of map is 8 bytes, not size of map, but size of each map entry. Each entry in the map will have 8 bytes. Can't I have an equation that transforms addresses instead of a map? Yes, but this would not be very flexible. This is actually what we had before with base and bounds. This is very simple, having an equation, but it's not very flexible. Where would this map be stored? This map has to be stored in physical memory, and this is a problem of future us. We have to figure out how to store this, and this is not trivial because this map could grow arbitrarily large. But for now, let's assume that we figured out how to store this in physical memory, and just think about the overhead for now. For now, we have, if we want to use 100 megabyte of virtual memory, we will need 800 megabytes of physical memory for our map, plus the 100 megabytes that we actually want to map in the physical memory. So we need 100 megabytes virtual to 100 megabytes physical, plus overhead of 800 megabytes. That means that we would need 900 megabytes of RAM to be able to use this system. So, actually, interesting. So for me it shows the full question, but apparently the Menti doesn't show the question. So that means that if we want to access 2 bytes in the memory, we need 4 pointers in total. Okay, let me think about this question a second. So if you want to access this pointer, let me take the pen because then you can see it better. This pointer, and maybe you say you want to access another pointer, let's say a pointer here. This pointer, pointer 2. Yes, for this pointer 2, we would need another entry here. This would have, again, 1 byte here. This is again 8 bytes of overhead to access 1 byte maybe here. Yes. But this will give us total flexibility here because we can map any byte to any byte here. A lot of flexibility. There will be no fragmentation because we can map any byte anywhere in the physical memory. Very, very nice. Then the conclusion that is written here in Menti is that so if we want to access 2 bytes in the memory, we need 4 pointers in total. For 2 bytes, you would need 2 virtual addresses, and they would be translated to 2 physical addresses. So the map would have to store in a total of 4 pointers. That is correct. That means 16 bytes overhead for 2 bytes. Absolutely correct, yes. For me, the boot process was way harder to understand than virtual memory until now. That's fine, because the boot process, you need that less in the practicals, and also if you need to look up something in the boot process. you will have enough knowledge about the boot process now that if you look something up there, you will be able to connect the dots. But for virtual memory, this is very, very central, and you will have to implement parts of that. For instance, copy on write. SWAP doesn't have it yet. You have to implement that. So this is why it's very important that we understand this in real depth. 1 byte is 8 bits, 4 bytes is 32 bits. Yes. Okay, could we just use an array of pointers to real memory, and the pointers we use are pointing to this array? We would only need half of the space. Oh, very nice. That's the first optimization. I really like this. This is great. We start ideas and with ideas, and we think about how we can optimize this. Yes, if we make this an array, we save half of the size, but we get into one problem now. So let's do that. Let's do this as the next optimization. I will continue here with this part. So this is all not usable. We can't work like that. Let's remove it. Okay. And you're saying we should use an array instead. Let's use an array. And now what we can do is use this pointer as an index, basically. Basically, this is just an array with how many entries? Well, 1 for every byte. So this array just has 2 to the 32 entries, because we need 1 per byte entries. And each of them is how large? 4 bytes. So that means that we need 4 bytes times 2 to the 32 entries, an array of this size for every process. So this is 2 to the 33, 34. So this would mean that we need for every process a physical amount of physical memory of 16 gigabytes required. Okay. Yeah, that's a problem. We only have 4 gigabytes, right? We don't have 16 gigabytes, but the idea is good. I like the idea. Thank you for pointing this out. We would only need we would have half as much overhead, but the initial memory requirement would be a much larger amount, because we cannot dynamically resize it or add entries, remove entries. Also, it would be easier to implement in hardware. A standard map, I can't implement the standard map directly in hardware. We can access 1 byte. Can we also access specifically 1 bit? No, we don't do that. We always, 1 byte is the smallest unit that we can access. And if we want to access 1 bit, we would have to mask that with some bit operations. Our example occupies 9 bytes in total. In physical, 8 for overhead, 1 for data. Yes, that is correct. And with this new example that we've just drawn, it would be 1 byte for the data and 4 bytes overhead. But the problem is the trade-off now is much worse, because we can actually not even create the map, because it requires 16 gigabytes and we only have 4 gigabytes. Wouldn't it make sense to create a bit mask to map virtual memory to physical memory? So you just do a bitwise AND or for mapping. I don't think this would give us the same flexibility. No, this would not give us the same flexibility. This would be more comparable to base and bounds then. The problem is in general that at some point we wouldn't have a big enough int that we could map for example 1 byte. I think I'm totally on the false path. Maybe so I think we will get to a more realistic design in a second. Let me skip this. We want to get there intuitively. Could you maybe use more of that interactive things in Menti, like the pro and con questions in the future? That was really nice. Yes, I will do that. When will the map be read? Only on context switches? Every single time the memory gets accessed. You're absolutely right. Every single time the memory gets accessed, we have to look up this map. So this gets really slow also, because for every memory access, we now have to perform 2 memory accesses. But still, otherwise we don't have virtual memory at all. So maybe that's the last part for today, and tomorrow in the assignment 1 tutorial, we have half an hour reserved in the beginning to also talk about page translation. So we will then continue there. And this always has been part of the assignment 1 tutorial, so I'm not adding any contents there. But it makes sense to have these basics before we do that. Okay. I saw one suggestion already on Menti, but also I think it was also in the chat. How can we optimize this? How can we bring this somehow, this number down, or how can we reduce the overhead in general? Because we have an overhead of now 4 bytes per single byte. That's not really good. No one would buy a computer like that with a factor 4 overhead. How can we reduce the overhead with a very simple trick? If the memory is stored continuously, we could use an offset. Maybe this 1 byte is a problem. Let's try what happens if we change this from 1 byte. Let's just change this from 1 byte to 2 bytes. Now we map a block of 2 bytes at once. 2 bytes here. Okay, now we need half as many entries. That's great. We need half as many entries. So only 2 to the 31 entries. And each has to be 4 bytes still. But that means we only need 8 gigabytes of RAM for this map. Oh, I think we are getting closer to a solution. Maybe 4 bytes is still not good. What would be a good size? Let's try a kilobyte. Let's try what happens if we do 1 kilobyte here. 1 kilobyte. Okay. 1 kilobyte. There's also the suggestion in the chat, gigabyte, using gigabytes or using 4 kilobytes. I will go through maybe one of these examples as well. Let's assume we take 1 gigabyte here. Then we would only have 4 different blocks. This would actually be worse than segmentation because it would only allow us to have 4 blocks of memory and only have 4 different permission sets, 4 different purposes for these things. So 4 is a bit, not enough. 4 segments, so a gigabyte is too large. Let's try a kilobyte. With a kilobyte, so that's 1024 bytes. We actually don't have 2 to the 32 entries, but because 1 kilobyte is 2 to the 10 bytes, we can deduce 10 here. So this would be 2 to the 22 entries of each 4 bytes. And that means that we have 2 to the 24 bytes of data overhead per process. So this is already a lot nicer. 2 to the 4 is 16, 2 to the 20 is megabyte. So this would be 16 megabyte. Oh, this is a lot nicer. 16 megabytes. Now, if we do this, if we map one block of 1 kilobyte, of course, this would also go to 1 kilobyte here, 1 kilobyte here, 1 kilobyte here to 1 kilobyte here. We would actually only need 16 megabytes. Aha, this is nice. So only 16 megabytes of overhead per process. Okay. Yeah, this is still maybe a problem if I run a lot of processes. Also, imagine you have a very small program, 16 megabytes of overhead for just a few kilobytes of memory that it actually needs is still a bad amount of overhead, still a lot of overhead. So what can we do? There's another trick that we can use here. Take a look at what we are doing here. We are taking some address space, map it to a table, and this table gives us the physical address. We can introduce, someone in the chat is already saying it, we can introduce more levels. Of course we can do that. And of course we can also choose different sizes here. Let's pick a different size. Let's pick, what would be a good page size? A good page size, 1 kilobyte doesn't sound so wrong, but maybe we can also take a look at this pointer, what this would look like. Let's assume we take a stack pointer. So a stack pointer in 32 bits would probably start with a 7, and the rest would all be Fs, or largely be Fs. Maybe there's a C at the end. C, F, F, F. This is 4, 8, 12, 16. Then we have 20, 24, 28, 32 bits. That's a 32-bit address. Now, if we say we want to use a page size of 10 bits, that's actually not nice to read. The offset in the page is not nice to read in this pointer then. And this is now something that they didn't tell you in ESP and in OOP1. A pointer is not an index in RAM. It's also not just an index in some table or somewhere else. A pointer is actually a struct with 3 numbers or more numbers. Let's take a look at this example here. So we make a cut here. Why do we do that? Because it's nice, because it looks nice. We have this nice offset with 3 hex characters. And at the same time, 3 hex characters, that's 12 bits. 12 bits. Nice. 12 bits, that's 4 kilobytes. Okay, we take 4 kilobytes here. We have 4 kilobytes here. Very nice. Oh, you can't see the 4 kilobytes up there. I'm sorry about that. Let me just write that down again, down here, 4 kilobytes. Okay. 4 kilobytes from here mapped to 4 kilobytes here. And these blocks have to be aligned. So you basically can number them. You have, you go through the physical memory and slice it into blocks of 4 kilobytes, and you do the same here. So you could compute something that we call a page number. You just count the how many, in German, die wievielte 4 kilobyte page it is. So you just go through there and then count and say, this is page number 520. And then here, this is page number 70, something like that. So it's just indices, page numbers. Isn't this basically what we learned in Con? Yes, I think you will have learned that in Con, but we go through this in more detail and we are far not finished. So we are approximately at half of what we want to build here. And tomorrow we will only be able to build the full 64-bit paging hierarchy. But yes, you might have learned that in Con already, or parts of it. So what do we do then? So we have one 12-bit offset here. And the nice part, this is what I really like about this, we didn't come up with any obscure definitions. There are no obscure definitions in here. We just made logical choices. The one didn't work, so we made a different choice. Why do we choose 12 bits here and 4 kilobytes? Because it looks nice, right? It looks nice. It was just an intuitive choice, and this is how we work here. Okay, 12 bits. And these, maybe I want to illustrate this a bit nicer. And this 4 kilobyte page here, this 4 kilobyte page, let me illustrate this also here. This is a 4 kilobyte page. 4 kilobyte page. Okay. And this has a lot of bytes. Okay. Bytes from 0 to 4095. And now we have the next problem. We need to store this map. If someone already said we want to have multiple levels, we need to store these tables somewhere. Let's start with the first table that we use. How large should we make this table? what would be easy to maintain? We sliced the physical memory into blocks of 4 kilobytes. So if we want to make this easy to maintain, we want to create a bitmap. We want to create a bitmap where we mark a block as used with a 1 or as not used with a 0. And then there's an intuitive decision on how large this, we call it the page table, how large this page table should be. And what is it? We make this page table 4 kilobytes so that we can easily say this 4 kilobyte block is in use, it's used by a page table. And that defines, because we still have our entry size of 4 bytes like before, how many entries we can have on this page table. How many is that? With 4 bytes and 4 kilobytes for a page table, we have 1023 entries here. That means that we have 1024, 2 to the 10. That means that we have to cut this hex character into multiple parts. This is the 10 bits here. Okay, this points us to some location here. We call this the offset. Okay, this next part, let's do like this. We call this the page table index, PTI, page table index, and this points us to some entry here. This entry gives us the address of the page as before. We had this before, right? It was pointing to the physical location. This is the physical location, and this points us there. But now we also have to find this page table because we don't know where it's in physical memory. So we add another layer. We still have bits left over here, and we just extend this design logically because we already implemented this part. Why wouldn't we copy paste it? So let's just copy paste it. And now we need a better name. Page table 2 doesn't sound so nice. Let's call it the page directory. And this page directory, how large is it? We want it to fit in this nice bitmap. So it's again 4 kilobytes in size. Okay. And it goes until 1023. And we take this, this value here and pass it as index into the page directory. This will be offset 7FF will be offset 511. And this offset 511 tells us where the page table starts, the physical address of the page table. And now we used up all the bits. The question is, how do we find the start of the page directory? This is now the only part that is still missing. So we have this pointer here. This is the pointer. Or actually, this pointer will be somewhere, this is actually fine. This is approximately the location of this pointer. Page directory, this is the page directory index. Where do we get the page directory base address from? Where do we get the physical address from where this starts? From a CPU register. The CPU just stores where the page directory is. Similar as in base and bounds, the CPU had to store in a register the base and the bound. Now we just have to store the start of the paging hierarchy, and we do that in the CR3 register on x86. And this is paging as it has been for a long time on 32-bit computers x86. Let's go through a few questions. I'm sure there are more questions, so let's answer them. Okay, one of the questions is, what's with paging by 4 kilobytes? That's what we do. 4 kilobyte pages, yes. Is with overhead for process meant usage of physical memory because this data structure is in physical memory? Yes, you are correct. This is exactly what we mean. 16 megabyte overhead per which unit? Per 1 kilobyte? Yes. So actually 16 megabytes of overhead, we already switched to this new design there where we had one page table, large page table per process. So it would be one per 16 megabytes per process in the example that we had before. But in this new example, it looks a bit different. But if the page table and page directory are 4 kilobyte in size, doesn't that mean that it goes from 0 to 4095? Oh, very good question. Let's take a look at what we have here. The problem is we need these physical addresses. And we have physical addresses here. This is a physical address, a pointer, right? And here as well. And here as well. How large do they have to be? How large are physical addresses? We still are in our 32-bit computer, so they have to be 4 bytes. They have to be 32 bits. And that means 32 bits here, we need 32 bits in this register. We need 32 bits in this entry. We need 32 bits in this entry, and this is a page then that we find through this. Let me just hide the Menti for a second, because otherwise you can't read it. That's why we have 1023 entries here, because each entry has 4 bytes. Okay, so now we intuitively derived how to create virtual memory, and we realized that this is exactly how the engineers designed it many decades ago. So that means we are actually quite clever that we come up with a design like this. Very nice. And I really like, this is also what I love about operating systems and these things. A lot of the decisions are very intuitive, because you try something, it doesn't work, you try it a bit different, and then it works, and then you realize this is how we've been doing it for 20, 30 or 40 years. So let's check if there are more questions on Menti. I do see more questions on Menti. Let's hide the video for a second. So basically the idea is really similar to caching, just in software. I don't know, this is actually not caching. This has a different effect. We are allowing to map small blocks of memory in virtual memory to small blocks of memory in physical memory. Caching has a different purpose and also does something different. So there might be some similarities in the way that you map addresses from one domain to another, but what is going on and what the purpose for this is completely different between caches and paging. Would it make sense to make the pages bigger with 64 bits, for example, 16 kilobytes? Yes, but the problem is we then run into backwards compatibility problems, because we would not be backwards compatible anymore with software that assumes 4 kilobyte pages. Now, if you would be a vendor that controls both the hardware and the software stack, which vendor could that be? Such a vendor could switch to 16 kilobyte pages. And guess who did that recently? Apple. They did that, and they switched to 16 kilobyte pages. Why do we need a page directory? Doesn't the page table already cover the whole 4 gigabytes with pages? For that, let me show you this one more time. And I have another nice way to show this, to give you some intuition of that. Think of a ruler like you had in school, a ruler where you had centimeters and millimeters and so on. You would have the same here. So this is a ruler, and you have here millimeters, okay, and then maybe centimeters and millimeters and centimeters and millimeters and so on. We're doing basically exactly the same here. One entry of this page directory, the first entry of the page directory, is this block. But this block is subdivided, and the first block here is then the first block in the first page table. So if you would only have a single page table, you would only be able to cover an area of this size. I hope that makes sense. If not, feel free to ask again. It wouldn't cover the whole 4 gigabytes. Actually, maybe let me go back to this. You can actually compute this. Let's compute this. So one page table has 1024 entries. One page has 4 kilobytes. So that means if all the entries in a page table are mapped, this page table maps an entirety of 4 megabytes. 1024 times 4 kilobytes, 4 megabytes. So this would allow you to map a 4 megabyte region of memory, not 4 gigabytes. With another 1024, you can map 4 gigabytes of memory. So if you think about it in a different way, each page table entry is responsible for a 4 kilobyte region and maps this 4 kilobyte region either to a 4 kilobyte page or not at all. Each page directory entry is responsible for a 4 megabyte page, for a 4 megabyte region, and either maps it to a page table or it doesn't map it at all. I don't understand what PTI and PDI do and how they are connected. The page table index, this is the index. This is the index that we use here. So if we do an array lookup, the page table, if you look at this in software, you will find this in SWEP, for instance. You can take a look at this in software. Page table has a data type. So you will have a page table entry array, an array of page table entries. PTI, the page table index, is the index that you use in this array, and this is the array entry that you want to get. Same for the page directory index. It gets you the right entry from this array. I hope that clarifies this a bit. And let's continue with the next question. How can we split the F character? Oh, then we get into hex computations. How do we do that? So let's do that. Okay. So this part is nice, right? Offset equals FC, and this would be, now we have to compute this, right? So I know that FFF is 4095, and C is, well, 4095 is FFF, then 4094 is FFE, 4093 is FFD, and 4092, did I miscompute this now? F5, E4, D3, C2. So this should be 4092 if I didn't miscount right now. Okay. So the PTI is the lowest 10 bits of this FFF. FFF. And if you want to take the lowest 10 bits, you can do something like end and then write a hex number that has 10 that has exactly 10 bits, but we can also do it like this. So let me write this down in binary if you want. I don't recommend doing this in the exam because you can introduce a lot of mistakes by doing that, but I will do this one time now. F, 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 and this is 1, 1, 1, 1, 1, 1, 1, 1, and this is also 1, 1, 1, 1. And we need only the first two, so the first two bits are gone because we don't need them, right? We cut them off because we only need 10 bits because this would be 12. So this means that we actually don't have an F here, but 2 bits will translate into 3. So the page table index is 3FF. For the page directory index, let's do this as well. So here we have a more complicated situation even because we need the last 2 bits from this F. So we would have something like 7F, and then there are 2 bits set here. So let's see what happens if we write it down like this. 7 means 0, 1, 1, 1. So if we put this together again, then we have these 4 bits here. This becomes an F. Okay. The next 4 bits, okay, become an F again. And then we have left 0, 1, which becomes a 1. So it's 1FF. That's how you split up these hex characters. Okay. is the idea of sectors, blocks on hard disks the same as this? There are similarities, but you also have a lot more flexibility because you can maintain this in a different way. In general, I would say, yeah, similarities, but it's also not. It's definitely not the same. It's not exactly the same. So each page table entry points to a single page, which is 4 kilobytes. Yes. In this architecture that we draw on the whiteboard there, yes. Drew on the whiteboard there, that's 4 kilobytes. Okay, that makes sense if each entry is 4 bytes, but why is each entry now 4 bytes and not 1 byte in the page directory and page table? Well, if you would take a look at this part here, this entry has to store a physical address. A physical address cannot possibly fit in 1 byte because we need to store 32 bits because we have a 32-bit address space here. So the physical address has to be 32 bits and we need to store them here, and that takes 4 bytes, 32 bits. So in 1 byte just would not fit. So the 12-bit offset tells us which values in the 4 kilobyte physical memory page we want to look at. Yes, exactly. What are memory banks and where are they involved? Memory banks you have in DRAM you have memory banks, but this is a topic that we cover in a different lecture. And for instance, in side channel security, we would talk about memory banks. This is not at all something that we talk about in operating systems. So the address is basically a path along the tables to the physical memory. I would say the address is a struct that provides you with a set of indices. In our example, 3 indices. One offset is the index within the page. The page table index is the index within the page table, and the page directory index, which is the index in the page directory. So it's a set of, in this case, 3 indices. What does each process need? Does every process need a separate page directory? Yes, a separate page directory and a separate page table or set of page tables. You will have 1 page directory per process, and you might have page tables, but you don't need all of them. So the overhead, we can also compute the overhead now. For each process, you need at least 1 page directory, which is 4 kilobytes. You might need a page table, but it depends on whether you map a page or not. So if you map a page, you need 1 page table. So the worst case overhead is that we have a process that only uses a single 4 kilobyte page. And then we need 4 kilobytes here and 4 kilobytes here. And that means we have an overhead of 8 kilobytes as compared to 4 kilobytes of data that we can use. So overhead of factor 2. So this is not good. But if we, for instance, have more than 1 page here, let's assume we have all the pages in this page table allocated, then it's already 4 megabytes that we mapped, and the overhead is still only 8 kilobytes. So this scales very well to larger memory allocations then, and the memory consumption does not increase. Or it increases as soon as we need a new page table. Okay. Okay. Every process needs 1 page directory. Yes, that is correct. Are these tables managed by the kernel? Yes, they are. The kernel writes the numbers in there to map all of this. And you will actually do part of this in the exercises. That's doesn't that sound amazing? I think it's really exciting. Is this part of a memory process by the processor itself? So what we do here is we configure the hardware. So these tables will be read by the hardware, but the operating system has to configure them so that the hardware knows where to find stuff. Okay. Why don't we combine the page directory with the page table? I'm not sure how this question is actually meant, but we do that. We first look up, so we take a pointer, and if the pointer is in this region, we will take a look at the first page directory entry. And then the first page directory entry can point us to a page table or not. If it doesn't point us to a page table, then the translation ends here and we don't get a page, and this will raise a CPU fault, a page fault. If we do get an address for this page table, then we go to the next level, right? So there will be many, many page tables for each page directory. And the page table then points us to the pages. So in some sense, they work together, but of course they are separate structures because they take care of different steps of the translation. I still don't get the role of the page directory. Yes, I'm also running a bit out of time, so we will repeat this again tomorrow. But if you can also rephrase the question a bit, I might be able to answer the question also. So does the kernel have its own page directory like processes? Yes, absolutely correct. Yes, the kernel has its own virtual memory, its own virtual address space. So it has its own page directory. Sure. We actually have seen that. We have seen in the boot process somewhere this kernel page directory. So this was what we've seen there. And with that, I would like to close for today. I see we have 2 more questions. Yeah, okay, then let's answer these 2 more questions. If every process has its own page directory, does the CR3 register have to be always changed when switching processes? Yes, absolutely. You're correct. We need a page directory to map bytes to a page table. We need a page directory to, so we need, we want to translate a virtual address to a physical address. And this is a multi-level process. We first take a look at the page directory, which tells us where the page table is, and the page table then tells us where the page is. And this allows us to create a sparse address space where not all the memory has to be allocated in the beginning. The problem that we had in the beginning where we would have needed 16 gigabytes of memory for every process. And now this is way more efficient. Okay, very good. With that, we are at the end for today, and I would like to thank you for your attention, and I'm looking forward to see you tomorrow, and I hope you are too. And then we will talk more about page translation and mostly assignment 1 and go through all the assignment 1 tasks. So looking forward to tomorrow and see you there.